last part, we discuss the pre-trained NLP model that you can use nowadays. Okay, so first let's start with the overview of natural language processing. Um, um, what is natural language processing? Natural language processing is a branch of artificial intelligence that deals with the interaction between computer and human language. So the thing you should be clear about natural language processing is a brand of AI, brand of artificial intelligence, right? So when we discuss about artificial intelligence, we might discuss about NLP, we might discuss about computer vision, right? So and other things, but okay, natural language processing is a brand of artificial intelligence, right? And it's specifically focused on the interaction between the computer and human language, right? So this is a key point to remember about natural language processing, interaction between computer and human language. So in this case, we need to somehow let the computer understand the human language and react to the human language input, right? So the purpose of natural language processing is to enable computer to read, to understand, and derive the meaning from human language. For example, this is some application of natural language processing in information retrieval, where we can have the search query and ask the computer to understand the query and return to us the reference the relevant document, right? And maybe in sentiment analysis, where we can have some comments, some feedback that we might collect from the internet and ask the computer to automatically classify the comment into different classes. Either the sentiment is negative, or they are positive, or neutral, right? And in information extraction, what we want to do is to have the computer model that can extract the key information from the document to build a knowledge graph, for example, right? In question answering, we want the computer really to understand the human question and then be able to answer the question that we ask the computer, right? And maybe to conduct the entire conversation dialogue, right? And maybe we want the computer to do machine translation, to translate automatically translate the language from French to English, for example, right? Okay, so let me recap again about natural language processing. Is the purpose of natural language processing is to enable computer to read, to understand, and derive meaning from human language. That means that we want the computer to have the same capability as the human to understand the language, right? And so that they can communicate with the human as the human to human, right? Okay, so the task of NLP could be one of the follow task type. The first task type is morphology, and in this task we focus on understanding how the word in the human language are constructed, such as the word prefix and suffix, right? So that in the language we have the verb and the verb in the passive sentence, right? Verb in to do whatever, right? And the second task type in NLP is a syntax task. So in this task we want to understand the relationship of grammatical structure between the word and phrase, right? So as we want to analyze the sentence to extract to know where the noun, where the verb, and where the adjective, whatever, right? So basically, it's the goal is to understand the relationship of grammatical structure of the word and phrase in the sentence and in the paragraph, right? We have other tasks of NLP is the semantic task. So in this task, the purpose is to understand the meaning of word, a phrase, and expression, right? For example, in this task, we want the computer to understand, for example, the synonym, right, and the intent of the sentence, for example, right? The other task is discourse task, and in this task, the idea is to understand the relationship between expression and sentence, right? So now we are not focusing on word and phrase, but in this task we focus on the discourse, consider the relationship between the expression and the sentence in that discourse, right? Another type of NLP task is pragmatic task, and in this task we would like to understand the utterance purpose and how to use the language in communication, right? And in the last NLP task type, the name is word knowledge, where we want to learn the knowledge about the word and the latent knowledge from the document and from the corpus, for example, right? Okay, the application of NLP is I think you can see there are a lot of applications of NLP, right? For example, we apply NLP in speech recognition, in text mining, to do the text clustering, text classification, summarization, topic modeling, question answering, right? And also for language tutoring, such as the automatic model that can correct the grammar and spelling when we typing, right? And also for in machine translation, right? For example, this is a machine translation application that actually implement the NLP model that can map the sentence in the short language to the sentence in the target language, right? This is an application of NLP in a conversation system, and the most popular example of a conversation system powered by NLP model is the Apple Siri system, right? With the system you can use on the mobile phone, and then you can ask a question, and then Siri will try to answer you, to try to reveal the correct answer, the appropriate answer to the question, right? And you can use this, for example, to ask, some question about basic knowledge that we can find in the internet, or you can add a series to schedule something for you, to call somebody or to send some message to somebody, right? And this is the example of NLP application in Google Search Engine, right? You can actually search not by the keyword. It's not a keyword search anymore, where the relevant document is returned to the user based on the, it's not that, the raw document, but you can add the specific question and the answer returned to you is not relevant document anymore, but it's actually the precise information about to answer that question. For example, here we ask about the director of Interstellar movie, and Google search can return to you, precisely the name of the director, right? Okay, it is an application of NLP in information extraction. So in order to return to you the correct information in here, actually, in the background, there should be a system to extract the information from document. The document could be the information about the movie on the Wikipedia, on the internet, in the document form, and the information extraction focused on extracting the key information in the document, and then build the knowledge structure. And from that knowledge structure, it will enable the search engine to answer the question precisely, as in the example we have here. Okay. Okay. So you might check. do some research on the word knowledge graph to see how they implement the knowledge graph from the internet, right? It's quite a very big system nowadays, powering the word search engine. Okay. So here's another application of NLP in doing tokenization of the text. So the idea, the purpose of tokenization is to split the text into sentence and word, right? If it is English, then the tokenization may be simple, so that you can do, space tokenization by space, white space. But for English, for Vietnamese, where we have only single word, where you have composite word, then the tokenization may be more difficult, right? Okay. Also, for part of speed tagging, the idea is to identify the word type of every word in the text. For example, this is the input sentence, right? And this is output. We want the post tagging return, so that it can detect that A here is the determinary, this is the noun, this is the auxiliary, this is the verb, this is noun, this is determinary, and this is noun, whatever, right? Okay. Another NLP task is the name entity tokenization, right? And this is quite a popular NLP task nowadays. The purpose of NET task is to sort and classify the text element, such as the word or the phrase in the text, into a predefined category, such as name of pupil, organization, place, time, monetary value, etc. Right? For example, here is our example, and we want to recognize the border visitor. Here is the organization. The US here is the location, and then Thomas Jefferson, then Madison, then Moore is a person. They are person, right? Okay. This is the syntactic parsing task. The purpose of this task is to do grammatical analysis of a given sentence according to the grammar rule. So it's somehow similar to the port tagging, but the output is not only the label for different token in the sentence, but also the tree structure, right? For the grammatical analysis of the sentence, right? Okay, this is a relation extraction task. The idea of this task is to identify the relationship between the entity, and this is considered the semantics analysis at a shallow level. For example, this is our input example, and we want the system to output the information, so that the relationship between this name and this operate organization, and this is the relationship we want to extract, and this is the president of the US, right? So this is a semantic analysis at a shallow level, that to extract the relationship between the entity in the text, right? We have a deep semantic parsing. So the task is not only to extract the relationship of the entity in the document, but also to somehow, convert the input sentence into some kind of executable format. For example, here, the semantic parsing here convert the input sentence into the lambda expression, right? So in this expression, you see it's like a mathematical formulation that it can be executed, and by executing formulation, it can return the answer for this, I mean, input sentence, right? So, okay. So that was the overview of NLP and different NLP application. Do I have any question about this part? Okay, then I suggest that we can stop for 5 minutes before going to the next part of the lesson. Okay. Ok, chúng ta tiếp tục nhé. Okay, now we discuss the second part of the lesson. Here we discuss about the word and text representation. To represent word and text in the past, we mostly use the WordNet. It is a dictionary containing the list of synonym and hypernym. This is an example of using the WordNet. For example, we can use the WordNet to find out the synonym set of wood. I mean, for example, here we import the WordNet from the NLTK corpus package. Okay, then this is the output where we can see all of the elements inside that synonym set containing wood, right? And this is an example of finding the hypernym of panda, right? For example, this is the result. The hypernym of panda could be the mammal, animal, organism, living thing, whole object, entity, whatever, right? So the WordNet have, I mean, it has some functionality that we see the demonstration here. Like you can find out the, for example, the word and synonym and its hypernym, right? But it have some disadvantages. For example, it lack of is the affluence. For example, we see that sacrifice mean death, right? But the nuance of sacrifice is different from the death, right? And also it have the it have no I mean entry for new word. For the word that find out in dictionary in teen language. That is something that we might not able to find the new word in the WordNet, right? Because the WordNet is something that I mean it created by the human, right? By the labor effort, right? So if there no effort to adding new word into the WordNet, you will not able to find the new word in the WordNet, right? And the WordNet depend on the subjective truth of the maker, right? So it's a human, it's a labor that I mean adding the entry into the WordNet. So it somehow really depend on the worker, right? And it takes a lot of labor to create and edit the WordNet. Right? As I told you, this is the human task, the manual task where we build the WordNet by having the real human seeing the word and adding the element to the WordNet, right? So it really need a lot of labor, a lot of human resources to maintain and to create the WordNet, right? So it's not a scalable way to, I mean, to build the WordNet, right? And somehow I even have the WordNet with the synonym, hypernym, and I mean some I mean information of the word such as now, adjective, whatever. We cannot calculate similarity between two words. There's no information in the WordNet to say if this word is similar, more similar to this word and than to the other word. Of course, we can say that okay, if the word are in the same synonym set, they are similar, but we cannot compare. Like okay, is it what is this word? Is it similar or is it I mean less similar to the other word, right? Okay. So to represent the word in the we can use it very simple encoding. Its name is one-hot encoding. And this mechanism represents the word as a discrete symbol where every word is represented by a vector. And in that vector, you see the special, I mean, pattern where you have a lot of zero and only one single element equal to 1. Okay, and the length of the vector is equal to the number of words in the dictionary. So the number 1 here is that the index, let's say the index of the word inside the dictionary, right? Okay, so the one-hot encoding here, you can see it's very easy to contract, to build the one-hot encoding for the word if you have a specific dictionary, right? But when you have adding more word to the dictionary, you need to re-encode every word, right? Because now the length of the dictionary is not, I mean, the same anymore. It's different, so that the vector will be different for every word inside that dictionary, right? And also the one-hot encoding cannot, represent, cannot allow us to calculate, for example, the similarity between the word, right? Because, for example, here the word motel and hotel, right? It is a one-hot encoding corresponding to the word, and you see if you do in some kind of mathematical computation on the two vector, you will get 0. That means the similarity is 0. But in reality, motel and hotel have very close meaning to each other, right? If you rely on the WordNet, and the WordNet I told you is not perfect, and it has many disadvantages. There's no new word in the WordNet, right? So somehow you cannot really rely on the WordNet for this kind of task, right? So solution for this, is to to have some way to encode the similarity in the vector representation of the word, right? Somehow better than one-hot encoding, right? Okay, this is another problem of one-hot encoding. It's about the vector size. The size of the vector is equal to the size of the dictionary. So if we have very big dictionary, such as the more than 13 million words, then every word will have the vector of 13 million elements. So it's too big, right? So somehow it's not suitable for bigger data set, right? Okay. Okay, so now we discuss a more popular way to represent a word. And in this approach, we represent a word by its context, right? Okay, so let's discuss the word context. So the word context is the surrounding of the word. In every sentence, every paragraph where we find out the word. For example, here we want to see the we discuss the word banking, and then the word around here on the left side and on the right side here are the word in the context of the banking, right? And that research, from a long time ago, 1957, is said that the meaning of a word is determined by the word that often appear in it, right? So it's so true that, for example, when you see the word banking here, it is reasonable to understand that, okay, the bank here, when we're talking about the bank here, we discuss maybe on the government debt, on Europe, on India, on regulation crisis, right? Okay, so so the idea about the context, about representing the word by context is named distributed semantic. So we in the approach of representing a word by context, we leverage the different context of a word to build its meaning, and somehow to build the word, perhaps to represent its meaning. Okay, the word vector. So in the word vector, a word is represented by a dense vector, right? It is different from the one-hot encoding. In one-hot encoding, you see it's the spare vector where you have that one element equal to 1 and the other are 0, right? But in word vector, here we discussed here, a word is represented by a dense vector such that the vector is similar to the vector representing other words that often appear in a similar context. Okay, so for example, the word banking, maybe we can have the vector for the word deaf, then the banking and the deaf, the vector may be, similar, right? Okay, so the word vector have another name. We can call them the word embedding or word representation, right? And nowadays, most people prefer to call the word vector as the word embedding, right? Okay, so here's the example of the word vector. You see, this is the word vector for the word part, and this is and the this is having the visualization of the word, maybe in 2D, in a 2D graph, and you see the words that are similar to each other are represented in a closed group than the word in other in the close and closer group than the words that are in have different meaning. For example, say, think, expect, see, right? And it is a being, been, right? And continue, become, remain, right? Okay, keep, take, make, get, one. Okay, so somehow this want to say that the word vector can represent the word as word meaning, all right? And similar word, right, have similar vector. The vector of say is similar to vector of think, so that they are close together when we plot the word in the plot, right? Okay. Okay, so now we can start discussing a very popular word embedding mechanism. This word2vec, and this research was conducted in 2013 by Mikolov and other author. So this is a method to learn the word representation. So this, as I want to say, that this is not the first word to represent the word by the word vector, but I mean the contribution of this word is, I mean, it's quite, I mean, quite popular, so that I mean people discuss about this approach quite often. So the idea of word2vec is to use a large set of documents, and we call the set document as corpus, right? As all the machine learning NLP problem, and it work in a fixed vocabulary is represented by a vector. And the idea of word2vec is to find out the word vector for every word in our vocabulary, right? So in order to do that, the algorithm, the approach here, travels a position in the text, it containing the center word C and the outer word content O, right? And it's used the similarity of the representation vector C and O to calculate the probability that O occur when C is present, right? Or vice versa, right? I mean, the probability we have C and then we find out O in the context, or when we have O in the context, the probability we have C in the center word, right? And the algorithm word2vec will tweak the word vector to maximize the probability, right? So this is like the loss function for our optimization problem. Maximize the probability we have to C and O, right? We have O if we have C, or we have C if we have O, right? Okay. So for example, here, for example, if we consider the contact window of side 2, that means that for every word we will only consider, I mean, 2 words in the back and 2 words in the front, right? Then we want to measure the probability of having the WT plus Z when we know WT. WT is the central word, right? And we want to measure the probability of this word, this word, this word, and this word, right? And then we move to the next word. We want to measure the probability of having the other word in the context, right? Okay. So here's the objective function of the word two-vector approach. So this is the likelihood function. So the likelihood function is calculated as simple as this formula. We do the joint probability of having, I mean, every word in the context of WT, right? We have T equal 1 to T, and then we have, I mean, this is Z. This is that T is the word in the dictionary, right? And this is M is the window side, right? We want to see the word, I mean, in the context window of side M, right? And here is the loss function. We want to maximize this likelihood function so that we minimize this, right? If to minimize it, we can, I mean, we do log over the likelihood function, and then we add the minus here. I mean, then we convert the maximize to be the minimize function. Okay, and by applying the log, we convert the joint probability to be a, I mean, to be a sum, right? We sum over from T equal to 1 to T and Z from M minus M to M, and log P W T plus Z given WT, and I mean theta, and theta here is I mean the weight of the model we want to find out, right? Find out the word so that we can maximize the likelihood and minimize its loss function, right? Okay, so how do we calculate the P, the probability of having WT plus Z given WT and theta? I mean, in that algorithm, they use 2 vectors for word W. I mean, if the W is in the center word where we considering the word, right? Then the W will have the vector VW, and when the W is the outer contact word, then we will have the word vector UW. So this is that technique that they use in the word2vec paper to make the computation more efficient. But I mean, of course, you can say that okay, use that one single vector for each word, but the complication may be more difficult. So in the end, I mean, to get back the single vector for every word, you can do so that you can average the VW and UV, sorry, and UW to have the final word vector representation for every word, right? Okay. Okay. Then I mean, then after we define the VW and UW, we can then with the center word C and the outer word contact O, right? We can measure the probability of having O even C like this one. And do you understand this mathematical formulation? So it actually the submark function, right? Let me check again. Okay, I remember that I did the slide, but okay, I don't find it here. So let me add one thing about the submark function for you. Okay, so do you still seeing my slide? Okay, so you see, this is it is actually the formulation for the submark function, because you have, the sum of probability of every word given C will be equal to 1, right? And this AP here is that the way we do the submark function, right? And V U0 UOVC here is just used to this is that the multiplication of UO and VC, right? And then we do AP and over this sum, right? And then we get back the probability. Okay. Okay, so then our word-to-vec model parameter will consist of every V and U for every word in the dictionary, right? So it's, for example, this is V and U, whatever, right? Okay, so we know that now we are clear about the model parameter, we clear about the objective, and we clear about how to calculate the PV here. Okay, so then we can apply normal stochastic gradient descent to find out the parameter, right? And any question? Any question for this part of the session? Hello. Okay, so if you have no question, then we might continue. Okay, so now we discuss, into detail about the word-to-vec algorithm. And the word-to-vec propose two model, the skip-gram model and then the back-upward model, right? So now we discuss the skip-gram model. So in this model, we have the dictionary size V, the number of words in our corpus, right? And we design the neural network, a very simple one like this. Well, the input layer is one hot encoding of the center word, right? And then, okay, so let me show you what is the skip program model. In the skip program model, we want to build hello, are you still hearing me? Hello.
Yeah,
okay. Okay, so let me repeat. In the skip program model, we want the model to predict the surrounding, word in the context given the central word, right? So the input of the model is the central word, here, right? And we want to predict, the probability of having the word in the surrounding context of the input central word, right? So the input layer, it is a neuron that has the input layer is actually the one-hot encoding of the central word, right? So the one-hot encoding here is just the mechanism to convert the word into the vector representation, right? This is not the word embedding, right? This is just a one-hot encoding, right? And in that neural network, we have one hidden layer with the dimension of n. So n here is actually the number of element in the word vector, right? And this is output layer, right? In the output layer here, what is the size of the output layer here? It have a CV dimension. Okay, so V is the dictionary size, right? So actually, this is so for every, every row here is actually the corresponding to the probability of one word in the context, right? Okay, so let's go back to the collection from the input layer to the hidden layer first. So we have the collection from the input layer to the hidden layer, and the parameter for that connection is actually a matrix W with the size of V n. Okay, so the k row of W is the central vector for the case word, right? Why? Because here we have the input is a one-hot encoding, right? And when we multiply the one-hot encoding with the W, where the one-hot encoding has that one element equal to 1 and the other is 0, so that the k row of the WV n is actually the center word for the k word, right? Is that clear? Is that clear?
yeah, it's okay.
Okay, okay, okay. Okay, now we discuss the second matrix, the W prime. Yeah, so again the k column of W prime is the contact vector for the case word in V, right? Because the output here is actually what we want to predict is we want to the output here, we want to return the actually the one-hot encoding of the word, right? Right, so this is a one-hot encoding of first word, second word, and then okay the C word, right? So in that case, the SI multiplied with the W prime equal to Y1 Z, and in this case I mean, Y and J is one hot encoding, so that the K column of W prime is the context vector for the K's word in V. Okay, so not that for every word we have two corresponding vector. Both of them are randomly initialized. Okay, so the word vector we want to learn is the matrix W and W prime here. So W will contain the word vector for the transfer word, and W prime contain the word vector for the word in the context, right? And as a normal, I mean, neural network training, we randomly initialize the ZW, right? And we want the training to optimize the W and W prime so that it can minimize the loss, right? Okay, so to train the skip RAM model, we can easily have the training sample by just having the source document. For example, in the source document, we can extract a sentence, and in the sentence, we can extract the training pair, so that we, for example, here, if the context window is the 2, then if we consider the here, then we have the and quick and the bro, right? Because we want the system to, if we input the into the model, we want to predict quick and bro, right? If we input quick at the input, we want to predict the bro and false. So this is our training example, right? The input and this is the route label, right? And again for every word. So it will be easy to contract the training data for this word2vec model, right? No labeling at all, because we can actually generate a lot of word pair, input word and then the predict word, right? Okay. So as you see in the computation of the probability here, we have the denominator is sum of the AFP of every, UW and VC, and it will take a long time to calculate, right? So in the word2vec model, they present all the optimization technique, and the most important technique they use to avoid calculating the expensive calculation is to use negative sampling, right? So by using negative sampling, they train the loss a little bit by having the loss is formulated this way. So this is this is probability for the correct word, and this is the probability for the negative sample. Okay, so let me try to explain to you clearer. So where instead of having the model to predict, the probability of the next word, in this loss function, they want to how to say to let me explain to you. They use negative sample so that the loss will be maximizing the probability for the correct sample and minimizing the probability for the wrong sample, right? So for example, here that you here's a use K negative sample. to add to the loss. And that means for every training sample, you have the input, you have the correct prediction, and then you have k negative sample. Negative sample means the word should not be in the context of t of the word of the word VC, right? Adding to the context, right? And here you see this. If you formulate the loss like this, you want to maximize the probability of having the correct word and minimize the probability of having the wrong word, right? And the PW here is actually formulated this way, and the third, this is just the hyperparameter, right? Do you have any question? Maybe I can re-explain to you. Hello? Hello, any question? Any question? So let me explain to you again. So the problem with with normal calculation of the probability of having O given C is like in this formulation, right? It is sum function, right? But the denominator here is quite expensive to calculate, so they try to tweak the loss function a little bit. So the loss function we have is here, right? Also in the beginning we have the ZT. What is the ZT? This is the ZT, right? Okay. And now we have the ZT like this, right? And in this ZT they have two parts. This is the part for the correct, word O in the context of VC, right? And this is a part for the negative sample of the word UZ in the context of VC, right? So it is named negative sample because the word U here is not in the context of VC, but we add them to the to the formulation of the loss to say that we want to maximize this part and minimize this part, right? So that maximize the probability of having the correct O in the context of C and minimizing the case when we have the wrong Z in the context of C. And the Z is chosen by the distribution here. Okay. So this is that the hyperparameter they use. You can choose that different PW as you want, but it is a configuration that the author find out to be the most efficient for selecting the negative word, right? Any question?
What is K in this loss?
What is what?
K. I from 1 to k.
K is number of negative sample. Number of negative sample you add to the loss.
Is this a hyperparameter?
Yes, it's a hyperparameter. For example, if we consider the center word bro, right? So in the context, the correct word in the context is the quick, fork, and dump, and the negative word not found in the context is, for example, lazy and dog, right? So we would like to add the lazy, dog, and other words in the computation of the loss, and we want to maximize this one and minimize this one. Any question?
Why we have the formula for JT like what? Like this?
For what?
What is the why we can refer the formula for JT like in the slide? Tại sao lại có cái công thức của JT như này ạ?
Tại sao lại có công thức của JT như thế này á? Đây là cái cách mà người ta define ra cái loss function thôi, đúng không? Theo như cái loss function trước, đúng không? Mà mình tức là define ra ở đây, đúng không? Thì rõ ràng là gì, nó sẽ là cái gọi là minimize cái này, đúng không? Cái nó này thì được tính từ cái đây, cái tổng chập với t từ 1 đến t. T đây sẽ là gì, tập tất cả các cái word trong từ điển nha, đúng không? Và với mỗi trong từ điển thì chúng ta sẽ là gì, tính một cái tổng chập của xác suất là gì với từng cái word đấy, và thì có các cái word ở context, đúng không? Context window chạy từ -m đến m, được không? Đấy thì với cái loss này, đúng không? Thì chắc là tức là gì? Thì với ví dụ nếu mà chúng ta nhìn trong cái network này, đúng không? Đây thì chúng ta hình dung này. Chúng ta muốn là gì? Với một cái input word, một cái word đầu vào, thì chúng ta muốn predict là gì? Những cái word ở đầu ra. Và maximize cái possibility là vì cái word ở đầu ra này chính là cái word ở trong cái context đúng không? Ví dụ ở đây là gì? Nếu chúng ta vứt đầu vào là cái từ quick này, thì chúng ta muốn rằng là cái probability có cái từ bro ở đầu ra này nó cao. Tức là gì? Ví dụ ở đây là gì? Chúng ta đây là cái đầu ra, nó là tương ứng với cái dòng thứ 1 ở trong từ điển đi. Đây nó là i1g mà, đúng không? Thì cái dòng này giờ không nói thứ 1 nữa. Ví dụ cái từ bro này nó là cái dòng thứ 2 đi, đúng không? Thì chúng ta muốn là gì? Cái output này thì nó sẽ phải bằng là gì? Cái softmax, xin lỗi là phải bằng cái one hot encoder của cái từ bro, của cái từ bro này. Mọi người hiểu ý tưởng ở đây không? Mọi người hiểu ý tưởng ở đây không nhỉ?
Cái này ok ạ.
Nó còn vấn đề gì nữa ở đây không? Đấy thì cái chỗ này là gì? Cái chỗ này là cái mà người ta đưa ra thôi. Tức là cái ý tưởng là gì? Là maximize, là ok, là ưu là context đúng của chúng ta. Cái O này là cái word ở trong context đúng ấy. Thì cái log của cái phần này là cao. Những cái phần với những từ sai ấy, thì là nhỏ. Okay, so let's continue. There are some result of multi-vec model. For example, after training the model, we can have the word vector for the male and female word, and king, queen, woman, whatever, right? And then you see when we plot in the graph, we can see that the relationship between the note that the point that represent the word king and queen, man and woman, they have some very root pattern, so that the direction from king to queen is somehow equal to the direction from man to woman. Again, from walking, walk, swimming, and so on. And it is a relationship between the different city and different country and the cities, right? Okay, this is another representation of word-to-vec result, where you see the word have a similar meaning closed in it represented in a closed group, and the word in different group have a distant meaning, right? Okay, another example of word-to-vec result. Okay, so in that paper, word-to-vec, if you read the paper, you can see they propose another approach. And in the previous approach, they have the they have the central vector and then predict the word in the context. And in the continuous back of word, they have the surrounding word in the context, and they want the model to predict the central word, right? So again, you have two matrix W and W prime, right? And the algorithm is similar to the Skipgram model. Okay, so maybe we can take a break for 5 minutes, and then we will continue. If you still have some question about word-to-vec, then we might try to discuss again. I believe that my explanation is not so clear to you, but somehow I hadn't found a good way to explain to you. Okay, so let's continue the lesson. Okay, so I will just present to you the word-to-vec approach to actually calculate the word vector for every word in the corpus, right? Now we studied different approach to calculate the word vector, and in this part we study a little bit about the word and co-occurrence vector, right? Okay, so first about the co-occurrence matrix. So the co-occurrence matrix represent how often a word occur in, for example, if it is how often a word occur in a document, then we have a term document matrix, right? So in the case we want to measure how often a word occur with another word, then we have term matrix, or word or co-occurrence matrix, or word context matrix, right? This is an example of term document matrix. So in that term document matrix, we have the cell in the table is the count of word, for example, word W in a document D. We have 1, 2, 3, 4 document, and this is the 4 word we have, right? And this is the count word in a specific document, right? So in this case, each document is can be represented as a count vector, a column, as you see here, right? And two documents are similar. We can use the vector here and to say that if the vector are similar, right, then two documents are similar, right? In the case of so for the word, so the document here is represented as a column in the matrix, and the word is a count vector represented as a row in the matrix. So for that over here, this is the representation for a word in this term document matrix. So we can apply the same semantic to measure the similarity of different words, so as to calculate the, to measure we can use the vector to calculate the similarity, right? So it would be represented as a row, right? So for the window-based co-occurrence matrix, or it have another name, word or word context matrix. So instead of instead of positioning the word with the entire of the document, we use a smaller context, so that the paragraph, or that a window, the surrounding window, like the first, the previous, like the window we consider have forward in the front and forward in the back, right? For example, here is a window-based co-occurrence matrix for our tiny example here. So this is the example. I lie in non-dependent NLP flying. This is the word, right? And we can set in our example the window size is equal to 1. Normally we have the window size 5 to 10, but to be simple, in our example we consider window size equal to 1. And here for every cell is actually the count number of time the word I is in the neighbor of the word enjoy, right? So okay, I put 1 here because I just found I enjoy here, right? I said the window size is equal to 1, so I don't consider this word, and this word, right? Again, for example, is okay here. I line. So there are 2 times the word I and line together. So I put high here. So in this case, again, every word can be represented at a row, right? Okay. And we can actually use this concurrent matrix to have the word vector for every word, and then we can use them to compare and to see if they are similar or not, right? But the concurrent matrix here have some problem. The size of the matrix increase as the word count increase. If we have a large number of words, then we need a lot of storage memory to thus keep the concurrent matrix, right? So in order to, reduce the size of the matrix or reduce the size of the word vector built on the concurrent matrix, we can use the dimension reduction mechanism. So for example, we can use a matrix factorization to actually, reduce, the size of the matrix to be 25 to 1000 dimension and equivalent to the word vector here. For example, we have the beginning, this is the concurrent matrix we have. We can use a SVD matrix factorization to actually factorize the matrix X to be W, sigma, and C. And we can use it, this sigma matrix here. Sorry, not this one, but we can use this matrix here, W, at the word vector for every word in the V. And now the size of the vector is K, right? Not V anymore. Okay. We have other work that try to leverage the concurrent matrix to build the word vector, and in this case is a growth method that combine the word2vec and concurrent matrix, and they have this specific loss function, and the loss function actually want to learn the word vector such that the dot product Wi and Wz equal to the logarithm of the word probability of concurrent matrix. So the Xiz here is actually the value inside that concurrent matrix, right? And they want to minimize this, right? Okay, for every I and J in the V dictionary. So the globe have some advantages such as it's very quick in training time, it's scalable for like couples, and it have good performance even with a small corpus and a small word vector size. To have more information about this, maybe you can check the paper growth, right? Okay, so I think that we can continue discuss the last part of the lesson for today, and then you can practice a little bit on word vector. Okay, for the pre-train NLP model, you can use the ZenSim package library. The installation is very simple as this command. Okay, and then you can download the data, and then you can split the data into maybe training and testing. Okay, then you can train the model with the data part 1, and then after training, you can have the vector for every word inside the dictionary. This is the word vector for the word topic, right? Okay, and you can use the model to calculate the similarity or get the top similarity word for a specific word, right? And you can save a new model, right? You can load the pre-trained model in ZenSim, FastTech, word2vec, growth, whatever, right? Easily found on the internet, right? Other pre-trained model that is more powerful than the BERT, XLLAN, right? But they are bigger and they mostly require CPU. Okay. So any question? Any question? Okay, if you have no question, then maybe we can come to the practical part. Okay. So let me send you the link. Okay, so you can study the documentation I sent to you in the chat window, right? It's a part of the Deep Learning 2 AI book I introduced to you in the previous class. So you can clone the notebook and try to understand it, and maybe to run to be more clear on the algorithm, what to do. Okay, so I may come back in 20 minutes to see how it's going.
Hello. Như vậy là thời gian học của chúng ta chắc là cũng kết thúc tại đây nhá. Thì chắc là tuần sau chúng ta sẽ tiếp tục. Chào cả lớp nha.
Dạ rồi thầy ạ.
Xin chào thầy.